Indefinite integral. Yesterday we looked at the definite integral. The reason it's called the definite integral is because we come up with a definite answer. We get some sort of number at the end of it. So the only difference with indefinite integral is that there are no limits on the integral. So it's like the primitive function where we have to include plus a constant. So there's not a definite answer because we don't know what the constant is unless they give us more information. Here's what's sometimes called a useful theorem. We can add 1 to the power over the power, but when we're doing this one, we also have to multiply by the coefficient of x underneath. So this little useful theorem, the reason it's useful, well, we don't have to expand the whole thing out. But it only works if that's a linear function. So it has to be a linear function to the power of n. So we got something like that. We don't have to expand. Of course, you could expand it out if you wanted to. But you don't have to. We can still add 1 to the power over the power, but this time we have to multiply the denominator by -5, the coefficient of x. So we'll get minus a 20th, 2 minus 5x to the power of 4. Plus, of course, a constant. It's certainly useful for something like this because how do you expand out something to a negative power? Because we'll have 3x plus 1 to the power of -2. But here we can do it using the useful theorem. Add 1 to the power over the power, but the denominator in this case has to also be multiplied by -1. Second last line there, mere mortal answer. Super mathematicians, of course, would go for the final line. Similarly with square root, because we'd have to put that into index form. And again, how would you expand out to the power of half? It's a bit hard. Add 1 to the power over the power, but this time the denominator is, where are we? Coefficient of x multiplied by 2. So we get 1/3, 2x plus 1 to 3 on 2, but again, mere mortal answer. We know that would be 2x plus 1 root 2x plus 1. Plus, of course, a constant. Okay, 5.